All right, welcome back. We'll go ahead and get started. Hopefully you had a chance to talk to all the poster presenters, get some coffee, etc. I'm very excited to welcome our final speaker for this year's workshop. Dr. Edward Johns runs the Robot Learning Lab at Imperial College, where he and his students study a range of topics in robot manipulation, especially looking at imitation learning, reinforcement learning, and using VLMs to generalizably solve these problems. Today, he's going to be giving us a different perspective on task and motion planning at Inference. So please take it away.
Great. Hi, everyone. Thanks for the introduction. So I don't really work in task and motion planning in the traditional sense. I'm trying to sort of been thinking today how to sort of merge task and motion planning and the work that I actually do. I thought I'd start off by kind of looking at the title of the workshop. So, Workshop on Language and Semantics of Task and Motion Planning. When I was looking at that, I thought, okay, maybe there are ways to sort of tease out some words here and kind of figure out how I can give a talk on this topic based on the papers over the last couple of years from my lab. So the first part of my talk, I'm going to talk about language and motion planning. Okay, so this is actually something I've worked on. It's not necessarily task and motion planning, but I have been looking into how we can use language models to do motion planning. So that's going to be the first part of my talk. Then the second part is going to be about visual semantics and how you can do task planning with VLMs, for example. So that, again, is something that I've been working on. So that higher level planning for multi-step tasks. And then for the imitation learning, I thought I'll just pretend that this workshop isn't called task and motion planning and just give a talk on imitation learning. But the particular imitation learning work we've been doing recently is for multi-step imitation learning, which itself is actually quite difficult to do with traditional imitation learning like behavioral cloning, because you need tons and tons and tons of demonstrations for multi-step tasks. So the imitation learning we do in my lab is it's all about efficient imitation learning from one demonstration, for example. So I'm going to be talking about that and trying to align that with the concepts of task and motion planning. So we'll start off with talking about language and motion planning. So this is some work we did. If you remember, a couple of years ago, it became very trendy suddenly to start thinking about how we can integrate language models with robotics. And there was a lot of kind of low-hanging fruit in terms of the kind of research that you could do. And it was like people had never done this stuff before. Suddenly, because of the ChatGPT moment, we could start looking into how we can integrate language models with robotics. So the first work we did on this was about answer this question: can large language models do motion planning? This question came out around the time when ChatGPT had just sort of come through, and people were saying, well, that's fine for like humans interacting with language models, but they don't know anything about robotics. They haven't been trained on robotics data. They don't know anything about the 3D world. They're just not going to be useful for robotics. And so we thought we would test that and see whether actually language models do know a little bit about the 3D world. Now, you've got to remember, this work was done about a year and a half ago. And in that period of time, language models have come a long way. But at that time, it wasn't clear whether language models really understood the 3D world and could do motion planning. So imagine this task here where you want to give a language command of wipe the plate with a sponge. The experiment we did was, can we design a single task-agnostic prompt? So this same prompt will be used for all the tasks that we want the robot to solve. And we're also going to give it 3D object bounding boxes. Okay, so this was before VLMs became very, very powerful. So we had to somehow feed in the poses of the objects to the language model. Okay, and we did that using an off-the-shelf object detection module, which we gave the language model access to. So when you say wipe the plate with a sponge, part of the reasoning is got to be to figure out what objects it needs to run object detection, the object detection module on in order to extract the bounding boxes. But if you look in the middle, we didn't want to give the language model access to any trajectory optimizers or any demonstrations or any action primitives, okay? We basically wanted the language model to do all of the trajectory optimization and motion planning internally using its own inherent knowledge of 3D space and concepts of robot trajectories. And then the idea is that we want to design that prompt such that the robot can then perform the task like on the right. Okay, let's see. Okay, cool. So now on the video on the right, this is what we want the robot to do. We want it to be able to perform that task that we just issued the command for. And it turns out actually this works quite well. With that single prompt, we're able to get these sorts of tasks to work. So tasks where you need to, the robot needs to have an understanding of the 3D nature of the world. So this is not just sort of 2D top-down kind of stuff. It's actually reasoning in 3D and understanding verbs, so shake. Okay, it's not a very good shake, and I wouldn't be satisfied if the robot shook a bottle like that in order to sort of mix something up. But it certainly understands that shake means going backwards and forwards. And wiping the plate means getting that sponge onto the plate and then moving it around. Remember, this is done about 18 months ago. So back then, the community wasn't sure whether the language models actually understood how to predict trajectories for robotics. These are the success rates. The actual success rate is not really the magnitude of each one is not that important because, of course, we've designed our own metrics and shaking the bottle, it was a success if it picked up the bottle and just went left and right, whereas that's not really shaking, is it? But we wanted to study the relative performance of different design choices, and so we need to come up with some kind of metric that allowed us to get a distribution of success rates across different tasks and across different design choices. So some of these tasks are pretty easy. So 100% for pick up the apple from the bowl and place it on the table. Pretty easy task for a language model to do. But something like pick up the bowl, if you see fourth from bottom, for some reason, that's a really hard task for a language model to do. And I'll show you an example of this now. So another thing that we looked into was failure recovery. Okay, so can a large language model plan a task and then realize that it's failed the task when it's executing it, and then recover from that behavior and actually try something differently next time? So here we've got this success detection prompt, which basically says, given the poses of the object as the robot observes them during the task, has the robot actually succeeded with that task? So it's got to figure out there, it's got the pose of an object and the pose of another object, and the relative poses of those. Has the robot succeeded or has it not succeeded based on those poses? And then we gave the language model or the overall prompt the ability to replan and retry the task if it fails, okay? And this is what it looks like when we run this. So here's the bowl task that I said has 0% success rate. So initially the robot fails to grab the bowl. All it's got is a bounding box, so it doesn't know about orientation, but it doesn't really need to know about that. But it should figure out that the edges of the bowl are important. And the second time, it has another go and it tries to grab the edge of the bowl, but it gets the orientation of the gripper wrong with respect to that edge. And then on the third attempt, it says, right, I've gone for the middle, I've also gone for the edge, but now I'm going to have a third attempt and I'm going to go for the edge and rotate the gripper by 90 degrees. So it has a deep understanding there of what is a good thing to try out next. So even if the first attempt wasn't successful and wasn't particularly sensible, it does understand how to try things that are different. So it has some understanding of that range of possible solutions. Okay, so that was our work on using language for motion planning. Now I'm going to talk about higher level task planning. So basically object poses. So can we do a sort of an inference-based approach for figuring out where objects should go, giving a language command of a task? And we started looking into diffusion models for this, so image diffusion models. So imagine this image here. You've got a knife, a fork, a plate, and a spoon, and you throw these in front of the robot. And you want the robot to orientate those objects and position them in a certain way that looks visually appealing. That's basically a tidying task, okay? So if we want the robot to tidy these objects, can we use an image diffusion model to generate the final goal image that the robot should then try to recreate? And this is, again, at the time when these image diffusion models were had just come out, and it was really amazing how effective they were at generating images. And one of these low-hanging fruit ideas was, let's use these image diffusion models to generate a goal image. So what we do here is we take the initial scene and then we figure out what the objects are in that scene. And once we've done that, we then generate an image using DALL-E in this case of those objects. Now, because if you were to go onto Google Images and type in a knife, a fork, plate, and a spoon, you would probably get much more images like the one on the right than the one on the left. You're going to get much more images of tidy scenes than untidy scenes, because most of these scenes have been had objects laid out by humans in a way that we want objects to be laid out. So you can actually use these image diffusion models to generate these nice, neat images that the robot can then recreate. Okay, and you don't have to manually define what those rules are, like you would have to do with classic planning. You don't have to define those rules that, you know, a knife has to go onto the right of the plate and the fork has to go on to the left, for example. You can just use that web-based prior that image diffusion models have been trained on in order to generate a natural and visually appealing image. So then what we need to do is we need to map back from the generated image to the real scene so that we know which objects in the real scene we need to move to match the objects in the generated image, okay? And basically this pipeline shows us how to do that. And what's going on is we're segmenting out the objects. That also gives us the names of the objects that we feed into the image diffusion model. And then we're going to use semantic features to match back the generated objects with the real objects. The reason we need to do that is because when you generate an image with an image diffusion model, it doesn't have any understanding of what object each generated object is. It's just some pixels, okay? So we need to find a correspondence between the generated image objects and the real objects. And once we've done that, we know we know where to move each of the real objects in order to recreate that generated image. When we did this, a little bit like the project with the language models, these image diffusion models were quite new and they weren't perfect. So we had to do a little bit of filtering. So initially they were generating these kinds of objects as well. So we had to have some heuristics to filter out those bad images. If you were to do this now, you probably wouldn't need to do that. I imagine you would get a perfect image that would just have a knife, fork, plate, and a spoon, and you wouldn't have to filter out these incorrect images. But at the time, that was a bit of an issue. You had to come up with a way to get rid of the bad images. And then you put this all together, and we have a system where the robot can tidy a scene without you having to define the rules about where those objects should go relative to each other. We're just using this web-based image prior, which has been trained on loads and loads of scenes of knives, forks, plates, and spoons. And that enables the robot to figure out what is a visually appealing image to then recreate. And we do have a little bit of hand-designed task planning here to know which order to move the objects in order such that they don't collide during this the movement of the objects. And then here are a couple more examples. So rearranging an office scene and rearranging some fruits into a basket. These are quite simple tasks, but the point is that we don't have to manually define the rules. We don't have to manually define a cost function to then do some optimization with. We can just use the web-based prior to generate that image and then use that as the goal image. So it's very, very scalable, whereas more traditional planning approaches, it's much harder to scale to sort of arbitrary objects that the robot might find in the home. We also looked into doing this in 3D. So image diffusion models, they work in 2D, right? You generate an image, it's a 2D image, might be from some viewpoint where things look 3D, but the actual image itself is 2D. So you don't get that depth channel, and you would have to infer the distance of the objects, which is quite a tricky problem. An alternative way to do that in 3D is to actually create a 3D reconstruction of the scene, and then imagine what that scene looks like in lots of different configurations. So here what we do is we say, right, we're going to scan the scene with a wrist-mounted camera and then build up a NERF, an object-centric NERF of that scene. So each object has its own NERF. And then what we can do is we can imagine what that scene looks like with objects in lots of different poses. So here we're imagining what the scene looks like if the pink milkshake bottle were to be placed in all of these different positions on the shelves. And for each of these generated images that we're rendering, we can then compare the clip similarity between that image and the language command. So if the language command is place the pink milkshake bottle on the top shelf, then this image is probably going to have a high score. And that's what you see in the top right there. We're seeing the heat map of those clip similarities. And that enables the robot to imagine what this scene would look like with these objects and all of these different poses, and essentially do that planning by imagining and then evaluating with its kind of clip-based cost function. And then you put this all together and you see the score heat map again on the top right, and then the robot just places the object where it has the highest score for that language command. Here are a couple more examples of the robot using that same method. Again, these are quite simple tasks, a bit like the DALI-bot work. But again, you don't have to manually define your cost function, okay? It all comes through these web scale priors, in this case, clip. So clip understands the similarity between a language-based description of a scene and an image visualization of that scene. Okay, so those are the works we did on language and image diffusion models for task and motion planning. I'm going to talk about multi-step imitation learning now. We've done a lot of work on imitation learning in my lab, particularly on efficient imitation learning. So if you take videos like this from companies like Figure, they're really, really impressive, but these robots take a long time to learn these tasks. Probably several days of data collection, followed by several days of training. Maybe this whole thing takes a month or so to actually collect data and train on it. But humans don't need to do that, right? Humans can be shown a single demonstration of a task, and then they can perform that task immediately afterwards. So I've always been very interested in that idea of one-shot imitation learning. How can we provide a single demonstration and get that robot to instantly perform that task? And we've been working on this for the last 5 years, and we've gradually got better and better at it. And this is our latest version. It's called Instant Policy. So here's my student Vitalis providing a single demonstration of a task. And then the robot is able to perform that task immediately afterwards without any training. The robot's never seen this object before or this task before. It's just instantly learned it. And it's a multi-step task here. So there's some kind of high-level planning going on in the robot's brain here. It's not just a sort of a simple reaching task. There is some planning going on, and it's reactive as well. You can see here we're moving the objects around and the robot is reacting. So how do we do this? It's all about in-context learning. Okay, so in-context learning is where you have a pre-trained model that you prompt with examples of the patterns that you want it to learn. So we can do that with large language models. So if you were to put this pattern in at the input of a large language model and ask it to complete the pattern in that bottom row, it would give you an answer. Now, in this scenario, what I've done is I've created each entry, each pair of numbers is a corner of one of these squares on the right, okay? And what it's doing, what I'm asking it to do is figure out what the coordinates are of the bottom right of that top right square. And it's able to do that. A language model will be able to do this very easily, okay? Humans, we can do it, but it would take us a while. As a language model, we'll be able to do this instantly. So we started thinking about, is it possible to do this with demonstration data rather than just numbers, okay? Is it possible to create some kind of model where you can prompt it with demonstrations and then instantly the model is able to predict what the optimal action is for that same task, but in a different configuration of it? I'm just going to summarize at a high level what this looks like architecturally. It's all based on graph neural networks. So the observations here, the green points here, these are the observations of the scene. The blue points are points on the robot's gripper. And then each demonstration is, each of these rows on the left is one demonstration. And then what the robot's going to do is going to condition on this plus the current state, okay? So the context to the demonstrations, and then we've also got the current state, and it's going to diffuse the optimal actions. We're using a diffusion process here to diffuse where those blue points, which represent the gripper, where they should move. And this works nicely because we're aligning observation and action spaces, okay? Observations are 3D points. Actions are also 3D points. They're in the same space, so there's nice regularization there, which makes it very efficient to learn. We didn't need to train this with any real data. Okay, the real data comes in when we provide that single demonstration at test time, but we didn't need to train it with real data. We could train it just with simulated data. And we use these pseudo demonstrations. So these are kind of arbitrary demonstrations of made up tasks that don't really mean anything, but they give the model the understanding of what does the same task in different configurations look like. So if the robot were to see these two demonstrations on the left and a snapshot of the demonstration on the right, the action on the right is what it should predict, okay? And we found that we can just train this entire model only on these pseudo demonstrations without any real data. And then once we've done the training and we deploy it, we can learn tasks instantly. So we're providing a demonstration of a task here, and the robot instantly is able to perform that task without having to do any training. It's just a single demonstration, no training, just conditioning or prompting that model with demonstrations. And again, it's this reactive closed loop policy here, which shows that the robot is continually looking at the images from its depth cameras and reacting accordingly. This is an interesting visualization which shows what's really going on in the mind of the robot, and is really, relating this to task and motion planning. You're kind of, the robot is thinking carefully about taking the current scene and sort of matching that back to the demonstration scene, and kind of figuring out where in the demonstration, what part of the demonstration does that correspond to the current live scene. So there's a little bit of implicit kind of planning going on here. And the attention weights here show the attention weights in that big graph neural network that I showed earlier. And if you watch the progression from left to right in the demonstration, or left to right on the testing, you'll see that attention starts getting applied more to the part which is just ahead of where the robot is. So the robot's looking back at the demonstration and thinking, okay, which part is just slightly ahead of where I am right now? That's the thing I really need to apply attention to. And that's the thing that I need to sort of really think about when I need to predict what the optimal actions are. And just to finish off, because this is a graph neural network, we can actually add in as many demonstrations as we like. So we trained it such that the robot can take in lots of demonstrations, more than one demonstration. So what you just saw there was a single demonstration on that big box, and then it failed to open that medium-sized box. It also fails to open this other medium-sized box. But what we can just do then is then add another demonstration for a third box, that time a small box, and now the robot's actually able to open that medium-sized box. So if you were using this in deployment, you could just observe that the robot is unable to perform the task and just instantly add another demonstration, and then the robot will instantly be able to perform that task. So you can just add in demonstrations as and when necessary, as opposed to thinking ahead about all the different configurations that the robot might need to have demonstrations for, waiting for the network to be trained on that, and then finding later on that maybe actually you didn't provide the right demonstrations in the first place. This allows you to just really observe the performance immediately, adding demonstrations as and when necessary. And that's the end of my talk. I'd just like to thank my team for working on this with me. And if there's time for any questions, I'd be happy to take them.
Thank you very much. Yeah, we've got time for a question or two. Cool. I have one. For the instant policy stuff, which I'm a big fan of, how sensitive are you to the nature of the sort of fake tasks? And what differentiates that training distribution from just uniform random motion or something like that?
Yeah, so you have to create those tasks such that they cover the kind of family of tasks that you're expecting to see in the real world. So the tasks that we have pseudo demonstrations for involved the gripper moving towards some object and then moving that object towards something else. So it's kind of picking up and placing, that sort of maneuver, but also tasks like opening a box. So you saw the example where the robot's opening the box. There's only one object there, but it's an articulated object, which is a little bit like having two objects, one object moving relative to the other. So that same distribution of data can also be used whenever there's a task which just has an articulation. But yeah, you have to think ahead about the distribution of tasks that you want the robot to perform, and then shape your pseudo demonstrations around that.
Very cool. Thank you. All right, let's give Edward another hand.